So good morning, everyone. This is EMI lecture number 1. My voice is not okay today. I hope I am audible as well as visible. You can hear me, right? Okay. So we are done with EM waves in the last lecture, and we have seen that EM waves consist of electric and magnetic fields. We have also seen Maxwell's equation. Now, when we saw Maxwell's equation, we saw that a changing electric field with time creates a magnetic field, and a changing magnetic field with time creates an electric field. How does a changing magnetic field with time create electric field? That gives rise to displacement current. How does changing electric field changing with time, it will create a displacement current. Now, this chapter is all about a magnetic field changing with time. And here we start this very interesting chapter known as electromagnetic induction. I'm sure you have heard about electromagnetic induction. Now, it all started with the experiment that Ørsted did. Ørsted, name of another scientist, in the year 1820. You might have seen this experiment in the chapter on magnetic field, the experiment of Ørsted. In 1820, Ørsted discovered the magnetic effect of current. He discovered that current produces magnetic field. Do we remember this? He produced magnetic field from current. He found out current produces magnetic field. All the scientists of that time, then they started thinking, is the reverse of this possible? Can magnetic field create current? That is what everyone was working on, and there were two scientists that were working on it day in and day out. Number one scientist was Faraday, and then we had a scientist called as Henry. And they discovered that indeed the reverse of this is possible. Current can be produced by a magnetic field. Faraday conducted some experiments in which he threw a magnet in a coil which was connected by a galvanometer, and when the magnet was passing through the coil, the galvanometer showed deflection. That means galvanometer sense current. That means magnetic field can produce current. Well, we can conclude the following observations from the experiment, and you must remember it. What did he discover? And we will be understanding them in great detail. He discovered that whenever the magnetic poles were moving towards the coil or moving away from the coil, the current induced was opposite. If the magnet was coming towards, current was something else in some other direction. If magnet is moving away, the current was in the opposite direction. If north pole is moving towards, current was in one direction. If south pole is moving towards, the current was in the opposite direction. Do you understand this? You also discovered that the galvanometer only showed deflection when the magnet was in motion. If the magnet was stationary, there was no current. More the velocity of the magnet, more was the deflection. When you increase the number of turns, deflection become more. If the resistance of the coil was increased, deflection becomes less. If the magnet is at rest, but coil is moving away or towards, the galvanometer always shows deflection. So he saw that whenever there is relative motion between the coil and the magnet, an EMF is induced in the coil. It induces an EMF, not current. If the coil is closed, if there is a circuit closed path, then current and charge are also induced. And he started calling this phenomena as electromagnetic induction. Do we understand this? Please note them down. I'll give you 2 minutes to do it. Let us move ahead and write Faraday's law of EMI. First law and second law. I am sure you have heard these laws. The first law says that whenever there is a change in the magnetic flux. Now, remember what is magnetic flux? Magnetic flux is the number of field lines. Number of magnetic field lines. Do we know this magnetic flux? If you have any surface, how many magnetic field lines are crossing that surface is known as magnetic flux. Whenever magnetic flux is changing with respect to time and EMF is induced in the coil, remember no current but EMF. And this EMF will be induced as long as the flux changes. So first law is still telling us that a flux is induced. The second law, however, tells us the value of this flux. This flux is proportional to the rate of change of flux. So E is proportional to d phi by dt, or we can write it as minus n d phi by dt, n standing for number of turns, n standing for number of turns, and phi standing for flux through one coil. Remember, flux through one coil, if it is given, then d phi by dt would be multiplied by n. If phi is the total flux, then we should not multiply by n. Do we understand this? I'll give you 2 minutes to note this down. When you are done, please raise your hands, okay? Let's move on to the next statement, and that is known as Lenz law. This Lenz law basically gives us the direction of induced current or the direction of EMF. The direction of induced current or the direction of EMF. It tells us that the induced current or EMF would be such that it always opposes the cause by which it is produced, which means that EMF is produced by changing flux. EMF is produced by changing flux. So this induced current will be trying to oppose the change in flux. Remember it. Induced current will be trying to oppose the change in flux. Induced current will oppose. Please write this in your sheets, in your notebooks. It will oppose change in flux. It will oppose change in flux. That means if flux is increasing, induced current will try to decrease it. If the flux is decreasing, induced current will try to increase it. Do we understand this? How does current induce? How does current change flux? How does it increase flux? How does it decrease flux? Remember, the easiest way to understand this is if it has to decrease flux, remember, if the flux is increasing, it will try to reduce the flux. How will it reduce the flux? It will reduce the flux. It will reduce the flux by creating magnetic field, in opposite direction. By creating magnetic field in opposite direction. If the magnetic field is going like this, it will create field like this. If the magnetic field is going inside the paper, it will create magnetic field outside the paper. Do we understand this? Then the next question is, how will it increase the flux? How will it increase the flux? It decreases flux by creating magnetic field in the opposite direction. It will increase flux by creating magnetic field in the same direction. Do we understand this? I'll give you example on this that will make it very clear. And in the formula, okay, just write this in your copy first, then I'll go ahead. I'll give you 2 minutes to do that. As I said that Lenz law gives us the direction of induced EMF. In the formula, we saw a negative sign. This negative sign tells us that the direction of induced EMF is opposite to change of flux. This negative sign is your Lenz law. This negative sign comes because of Lenz law. Do we understand this? I'll give you a minute to note it down. Now remember, in many questions, what we have to do is to find the direction of current. Now, to find the direction of current, I'll give you some basic concepts. I have already told you, but here I will give you that in writing so that you can note it down. What are the key concepts for finding out the direction? Number one, you will have to look for flux change. Flux change means you will have to see whether the flux is increasing or flux is decreasing. If the flux is increasing, we'll have to oppose it. The flux is increasing, I'll have to decrease it. If the flux is decreasing, I will have to increase it. Do we understand this? Yes or no? If it is a closed circuit, we will have current. If it is not a closed circuit, we will only have induced EMF. Do we understand this? So these are the 3 points that you should remember. I'll also discuss in very brief what is flux. Give you 2 minutes to note down these important points, and then we will find out direction of current when the flux is changing. We have been talking a lot about flux. Let me give you a small glimpse of what is flux. Magnetic flux. Magnetic flux. What do you mean by magnetic flux? It is the number of magnetic field lines crossing a surface or an area in a direction perpendicular to area. Do we understand this? Suppose I have a small surface like this. Let me call it ds, small surface, or dA. This small surface is placed in a magnetic field. So what will happen is magnetic field lines will be crossing this surface. This is the magnetic field and this is the magnetic field lines. It will be crossing this surface. The number of field lines which cross this surface is known as magnetic flux. Magnetic flux is denoted by the letter phi, and it is a scalar quantity. Do we understand this? Through this small area, the flux d phi, small flux d phi, will be the dot product of B and the area. Remember, area is taken as a vector in physics. The direction of area is taken as perpendicular to the area. For example, if the area or surface is like this, my hand is a surface. The area vector for this surface, we call it area vector, will go like this. Do we understand this? If my phone is a surface, the area vector will go like this or like this. Do we understand this? My bottle is a surface. Here area vector is going here. 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 Do we understand this? This is the formula for small flux. To get the total flux phi, we integrate it and we write it as B dot dA ka integral. If everything is constant, we can write the value of flux as B into A into cos theta. Where what is cos theta? Cos theta is the angle between magnetic field vector and area vector. Do we understand this? Please note it down. Very important point. I'll give you 2 minutes. Once you are done, please raise hands. So we have seen what is flux. Phi is the flux. It depends on 3 quantities: magnetic field B, area A, and angle. Now, if I have to change flux, I can change it by changing the magnetic field, number one. Number two, by changing the area. Number three, by changing the angle between B and A. Do we understand this? Or I can change any two. I can change B and A. I can change A and theta. I can change B and theta. Or I can change all B, A, and theta. Do you understand this? Now, if I increase B, or increase A, or increase the value of cos theta. Remember, to increase the value of cos theta, I have to decrease the value of theta from 0 to 90. Do we understand this? Cos 0 is 1, cos 90 is 0. Theta is increased, cos theta decreases. Yes or no? All these things will lead to my flux increasing. Do we understand this? If I do the reverse, flux will decrease. Remember, by Lenz law, if flux is increasing by Lenz law, what I need to do? What the induced EMF will do? Induced EMF will try to decrease flux. Do we understand this? Flux is increasing, induced EMF will try to decrease flux. How will it decrease flux? By creating magnetic field in the opposite direction. Do we understand this? If I do the ulta of this, if magnetic field is decreased or area is decreased or cos theta is decreased, that means theta is increased, your flux will decrease. Then what will it do by Lenz law? What will the induced current do? It will try to increase the flux by creating magnetic field in the same direction. Do we understand this? Do we understand this? I'll give you 2 minutes, note it down, read it, and now after that we will find out direction using Lenz law. I'll give you 2 minutes. Okay, let us try to understand how do you find out the direction of induced current by some examples. Let me take example number 1. A simple example where I have 3 wires and I have a moving wire which is moving like this. Now here I have a magnetic field which is pointing in the downward direction. Do we understand the scenario? 3 wires placed in a magnetic field. The 4th wire is moving. Now you have to find out the direction of induced current. How do you do it? You ask some questions and you find answers for that question. Question number 1. Is there Is there any flux linked with the coil? Is there any flux linked with the coil? Remember, there is magnetic field and you have an area as well. This is the area it is enclosing. B multiplied by A will give you the flux. Sometimes the wire or area may not be in the magnetic field. In that case, the flux will be zero. In some cases, the angle between B, magnetic field and area can be 90 degrees. In that case also flux will be zero. What about in this case? Is there flux in the coil? Thumbs up. Or is there no flux in the coil? Thumbs down. There is magnetic field. There is area also. So is there flux in the coil? The answer is yes. Do we understand this? Do we understand this? The second question is flux changing? Is flux changing? As you can see, this coil is moving like this. So the flux will change because the area will increase. Yes or no? So the flux is changing. Yes. Yes, the flux is changing. Then the next question is it increasing or decreasing? Tell me, is it increasing or decreasing? Area is increasing, therefore flux is increasing. Yes or no? No or yes? Then we have to apply Lenz law. If the flux is increasing, we have to oppose it. That means we need to decrease this. Yes or no? No or yes? Now, how do we decrease flux? By creating magnetic field in the opposite direction. So I have to create magnetic field B in the opposite direction. Here, magnetic field is going inside. I have to create magnetic field outside. Do we understand this? To create magnetic field outside, magnetic field should be coming like this. I apply right hand rule to create magnetic field outside. My hands will move in this direction. That means the current will come in the anti-clockwise direction. Do we understand this? The current will be coming in anti-clockwise direction because if the magnetic field has to go inside, current will go like this. The magnetic field has to come outside, current will go like this. Do we understand this? So the direction of current here would be anti-clockwise, and this is how you find out the direction of current using Lenz law. Do we understand this? Do we understand this? Okay, then I'll give you a minute to note this down, then we'll solve one more question. So now I'm going to give you a question, and the question is like this. Again, there is a coil which is moving inside a magnetic field. The magnetic field is coming outwards. The coil is moving like this, and I want you to tell me the direction of current in the loop. I'll give you 5 minutes to think about it. Think about it and give me the answer. Okay, let me help you out. We will ask questions and you will give me the answer. Question number 1. Is flux linked? Yes or no? This is yes, this is no. Is there a flux link in the coil? Yes. Is flux changing? Is flux changing? Yes. No. It is changing. You can see this is magnetic field. This is area. When I move the coil here, the area becomes less and less. Do we understand this? Flux is changing. Yes. Why? Third question. Can you do it now? Is flux increasing or flux decreasing? Increasing, decreasing. The flux is decreasing because area is becoming less. Area of the coil is becoming less. What does Lenz law say? It says that you change flux, change the opposition of flux. The flux is decreasing, so we need to increase it. Yes or no? How do I increase the flux? By creating magnetic field in the same direction. That means magnetic field has to come out. Magnetic field is out. We have to create magnetic field in the same direction. It has to come out. Do we understand this? To create magnetic field in the outward direction, the current should move in the anti-clockwise. And therefore, the correct answer is number 1. Do we understand this? I'll give you 1 minute to note it down and then I will give you the next question. Well then, I give you the next question and I give you 3 minutes to solve it. Remember, if a question comes from Lenz law or EMI, these are the type of questions that will come. 3 minutes, question is there for you. So how do we do it? Step by step. Number 1, is flux linked? Yes or no? Is there a flux in the coil? Yes. Number 2, is flux changing? Yes. Is flux increasing or decreasing? Great. It is decreasing. What does Lenz law say? Oppose. Flux is decreasing. What we got to do? Increase. How do I increase flux? By creating magnetic field in the same direction. The direction here is inside. So I have to create magnetic field inside. Do we understand this? To create magnetic field inside, what is the direction of current? Do we understand this? That is the correct answer. clockwise. Not a problem. We'll give you one more. Can you do the next one now? Okay. Here comes the next one. I'll give you 3 minutes to solve it. I hope you can do it. Answer, ask the same question, find out the answers, and you will do it. Have faith. In this case, remember, magnetic field is between the two lines. Magnetic field is going inside. The next question, 5 position of the coil is given. As you can see, here is the coil A, B, C, D, and E. We'll have to find out the direction of induced current in all these 5 positions. The first question is for position A. I'll give you 5 minutes to find out the answer for position A. Okay, then let's talk about point A. Is there a flux link in the coil? Yes? No? And the answer is no. Remember, magnetic field is not here. There is no magnetic field. If there is no magnetic field, there cannot be any flux. If there is no flux, you don't go ahead. There is no current. Do we understand this? Yes or no? Give me big hands up that we understand this. I'll give you 2 minutes again to think about position number 2, position number B. 1 is anti-clockwise, 2 is clockwise, 3 is no current. What is the answer for case number B? Tell me. 2? Clockwise? Okay, let us see. We're talking about case number B. First question. Is there a flux link with the coil? Yes or no? Yes. As you can see, there is some area which is inside. So yes, flux is there. Congratulations. Number 2. Is the flux changing? The coil is moving inside. The coil is moving inside. Area inside the region will increase and hence flux will change. Yes or no? Now the next question is the flux increasing or the flux decreasing? Is the flux increasing or the flux decreasing? Flux is increasing. Flux is increasing. Flux is increasing. So what does Lenz law say? Opposite. Lenz law says opposite. How do I oppose it? By creating magnetic field in the opposite direction. Decrease it. Yes, decrease it. By creating magnetic field in the opposite direction. Magnetic field is inside. I have to create magnetic field outside. Right hand thumb rule. To create magnetic field outside, the current will go anti-clockwise. That is the answer. Just remember this: to create field outside, please note it down, anti-clockwise, inside. Do we understand this? So the answer is anti-clockwise. Here comes the next question. Question number 3 for C, point C. I'll give you 2 minutes to solve it. So what is the answer for case number 3? Clockwise, anti-clockwise, no current. Tell me the answer. 1, 2, 1, 2. What is the answer? Let's start. Let's start by asking question. Question number 1. Is there a flux linkage? Yes or no? Yes. This coil has an area. It is inside a magnetic field. There is a flux linkage. Flux is there. Yes. Question number 2. Is the flux changing? Is the flux changing? Is the flux changing? And the answer is no. No change in flux, so no current, so no EMF, no direction. We write it: rate of change of flux, d phi by dt is 0. Flux is there, but it is not changing, and therefore the current is 0. Do we understand this? Yes or no? Well done. Then I will give you 2 minutes to solve the next case. Case number 4. Case number D. Have you got the answer? Anti-clockwise, clockwise, 0. What's the answer? Let's see. Let's ask questions. Number 1 question. Is there a flux linkage? Yes or no? Yes. Number 2. Is flux changing with time? Question number 3. Is flux increasing or decreasing? Decreasing, yes, because area is slowly going to become less and less. Flux is decreasing. What does Lenz law say? Oppose. So I have to increase flux. Yes or no? To increase flux, I have to create magnetic field in the same direction. I have to create magnetic field in the same direction. Inside, that means current has to be clockwise. Clockwise is the answer. Did you get the answer? Well done. Great. That takes us to the last part of this question. The last segment. Give you 2 minutes to find out the answer for this. Let's see if you can get this. Question number 1. Is there a flux link in the coil? If it is 0, then we don't go any further. The current is 0. Do we understand this? Well done. At the end, we have understood the concept of Lenz law. In today's class, what we have done is we have understood what is magnetic flux. Magnetic flux is a number of field lines which are passing through a surface. B into A into cos theta. You can increase flux by increasing any of these. You can decrease flux by decreasing any of these. Lenz law states that the direction of induced current or EMF will be such that it opposes the change. The flux is increasing, you need to decrease it. By creating magnetic field in the opposite direction, the flux is decreasing. You need to increase the flux by creating magnetic field in the same direction. If the magnetic field is inside, current is anti-clockwise. Current is clockwise. The magnetic field is outside, current is anti-clockwise. Do we understand this? Well, on that note, I'll wind up today's class. I'll see you in the next class. We'll go ahead with more discussion on EMI. I hope you will practice the question that I have done today. In case of any doubts, I am always there. Take care and have a nice day.